far out into the darkness, a single ember speckles against the black. The very last star. Inching through every remaining scrap of fuel it could find, it has eked out a meager existence for trillions of years. But slowly, inevitably, it fades, thus bringing the curtain down on the greatest show the universe has ever known. All that remains are relics of a bygone age. Black dwarfs, neutron stars, and above all, black holes. These stellar corpses but eerie reminders of the joys of youth. But they too are mortal, and after an inconceivably long time, even they flicker and vanish. Now the ancient universe appears empty. But it is not. For there are still monsters lurking in the shadows, monsters called forth by the ocean of quantum waves that fill the cosmos. And this is particularly true if time never ends. If it is infinite, then every possible quantum fluctuation is guaranteed to play out eventually. Given enough time, quantum fields will occasionally arrange themselves into fleeting pockets of order. A stray atom here, a complex molecule there, a warm clump in a cold void. Indeed, there is no principle that forbids such accidents. Only the low odds delay them, and infinite time is merciless, even with the lowest odds. And if we follow this logic far enough, it leads somewhere deeply unsettling. For if order can arise by chance, then so can experience. A flash of awareness assembled from chaos, not born of stars or planets or evolution, but conjured briefly by quantum fluctuations and statistics alone. And in an eternal universe, the familiar cosmic story, the one of galaxies, biology and history, risks becoming the exception rather than the rule. After all, endings matter. Endings give us meaning. Without them, things quickly become very strange indeed. In 2023, space probe Voyager 1 had a problem, 46 years into its journey away from the Earth. And so NASA's Jet Propulsion Laboratory worked on a fix for months, and despite the probe being over 15 billion miles away, hoped to move the corrupted code elsewhere on its system. And on April the 20th, 2024, the mission flight team received data back from Voyager 1 from interstellar space, showing they'd been successful. Sometimes it's useful to be able to control something remotely, even from the other side of the world. And if you're looking to remotely control your computer for personal or business reasons, AnyDesk can help. AnyDesk is a lightning-fast remote access tool that makes it feel as if you're sitting right in front of the remote machine. We find it especially useful for video editing. Our editors can access their high-performance desktops back at home, wherever they are. AnyDesk's proprietary codec technology ensures minimal lag and crisp visuals, even over slow or unstable internet connections. This allows us to keep digging into projects, even when traveling abroad or on a relation's rural Wi-Fi. AnyDesk is available across all major platforms, is backwards compatible with older operating systems, and has 99.98% uptime reliability, so you can depend on being able to use it when you need to. And what's more, personal use is totally free, with tailored plans for team and business environments. So head to anydesk.com to try this premium remote access tool, free of charge. Dawn rises slowly over the terracotta rooftops of Prague. In the half-light, a bell tolls and a crowd shuffles towards the old town hall, where something special is about to take place that has happened hour after hour, day after day, for more than 600 years. Two small windows swing open, and intricately carved model apostles begin their slow procession above the square as the bells ring out. But the true marvel sits beneath them. an intricate dial of brass and blue enamel crowded with symbols. The sun, the moon, constellations marching in lockstep, and below that, another great wheel showing the saints' days and seasons of the year. For 6 centuries, the Orloi astronomical clock has tried to tame the most elusive thing humans have ever tried to measure: time. It has outlasted fires, floods, plagues, empires, and the artillery fire of Nazi tanks. Through centuries of chaos, this mechanism has kept on ticking, insisting that time flows cleanly from one moment to the next. But what exactly is the clock tracking? What is time? And more importantly, will it ever end? To find out, we return to the clock itself. Its great dial is flanked by 4 carved painted figures: the astronomer, the philosopher, the angel, and the chronicler. Each offers a different answer to time's most unsettling questions, and together they form a kind of council, a medieval chorus presiding over the true nature of past, present, and future. And we begin with the astronomer, asking him a simple question: what lies ahead for the universe? Will the cosmic clock continue to tick forever? Does an infinity of tomorrows stretch out before us indefinitely? When the Orloi clock was built, many origin stories were being told around the world. A 6-day creation, the biblical Garden of Eden. Yet in the East, Hindu, Buddhist, and Jain teachings spoke more of repeating cycles, often with no absolute beginning. However, today, standard cosmology argues that time doesn't stretch back infinitely far into the past. Instead, there was a definite start, the moment the universe took its first breath, the Big Bang. Around 13.8 billion years ago, space and time simultaneously flashed into existence as the newborn universe expanded rapidly, and it's been expanding ever since. And so the secret to unlocking the universe's future, and the question of whether time is indeed infinite, lies in deciding what will ultimately happen to this expansion. And one man, an overlooked giant of 20th century cosmology, was amongst the first to consider this idea in detail: what will be the ultimate fate of our universe? His name was Richard C. Tolman. Tolman's career is a study of 2 parallel paths: a quiet, fiercely intelligent, practical man whose first love was the search for scientific truth, but whose unique skill set made him invaluable when geopolitics brought the world to war. In the First World War, Tolman joined the Chemical Warfare Service, and by the Second World War, he was advising the Manhattan Project on how to build the atom bomb. But before the bomb, Tolman quietly became one of the world's foremost experts on Albert Einstein's general theory of relativity, at a time when it was still largely unfashionable. 12 years before, the Soviet physicist Alexander Friedman had shown that Einstein's equations permit a universe that initially expands, but then reaches a maximum size before recollapsing back down to nothingness. But in a landmark 1934 paper, Tolman showed that such a collapse wouldn't break any of the sacrosanct laws of thermodynamics. He showed that the Eastern ideas of repeating cycles were also possible, an endless oscillation of expanding and contracting universes. Tolman legitimized the possibility of these collapsing phases, an idea known today as the Big Crunch. In such a cyclic universe, time may not be infinite. Instead, the cosmic stopwatch would regularly be reset back to zero. Although the trouble is, we don't seem to live in such a universe. And the story of how we came to discover this begins with a simple question: how do we measure distances? Astronomers often use objects known as standard candles as cosmic yardsticks. These are objects that all share the same inherent brightness. If we look up at the night sky and see dimmer or brighter ones, the dimmest must be the furthest away. Cosmic explosions, known as Type 1a supernovae, are particularly powerful standard candles. They detonate when a dead star, called a white dwarf, approaches a critical mass and blows itself to smithereens. Indeed, Type 1a supernovae are so bright that they can briefly outshine an entire galaxy of billions of stars and can be seen from halfway across the visible universe. In the 1990s, most astronomers assumed that the expansion of the universe was slowing down as the initial impetus from the Big Bang faded. If true, scientists realized that this would lead to Type 1a supernovae appearing clear and bright. After all, they wouldn't be carried away from us as fast as they once were. However, two teams studying them found the complete opposite. The supernovae were too faint. They'd been rocketed away from us faster than expected. The expansion of the universe wasn't slowing down, it was speeding up. The news sent shockwaves through cosmology. Decades of assumptions and theories were consigned to the scrap heap. The Big Crunch and the cyclical universes it could lead to were practically erased from the textbooks as a possibility for our universe's future, and in 2011, the scientists heading up the two teams shared the Nobel Prize in Physics for the landmark discovery. This accelerating expansion is usually put down to a mysterious and shadowy entity known as dark energy. No one knows for sure what it is, but what we do know is what's likely to happen to the universe if dark energy continues on its current trajectory unchecked. Dark energy seems to function as a form of anti-gravity and appears to be a property of space itself. And so as it expands space, dark energy's potency may only grow, expanding space yet further. The space between stars could stretch to such an extent that entire galaxies would be torn apart. Then the space between stars and their planets, leading to the dismemberment of every solar system. This accelerating expansion could continue until even the spaces between the parts of an atom grow unbearably large. All structure in the universe would eventually be destroyed. Astronomers refer to this cataclysm as the Big Rip, and in some estimates it could reach its crescendo in as little as 22 billion years' time. And if that's true, the universe is already almost 40% of the way through its meaningful life. Indeed, the expansion doesn't just get faster, it runs away with itself. The rate of expansion keeps steepening until the size of the universe grows without bound, racing to infinity in a fixed amount of time. You reach a moment beyond which the equations of general relativity, the ones that describe the marriage of space and time, simply stop making sense. A singularity. There is no way to continue the story of the universe past this point, not just because clocks themselves would break, but because there is no space-time left to put more time into. In a big rip, the universe doesn't just end in ruins. Time itself runs out. However, this nightmarish scenario is far from guaranteed. It all depends on an important cosmological measurement known as dark energy's equation of state, often denoted by the letter W. This is a measure of how strongly dark energy drives the expansion of the universe. The more negative W is, the more the repulsive energy in empty space grows as the universe expands. And so time will only end in the infinite muddle of a singularity if dark energy's equation of state is less than -1. Only then will the dark energy in each cubic meter of empty space increase as the universe expands, adding to its potency and triggering that runaway surge towards the end of time. Astronomers refer to this particular breed of dark energy as phantom energy. And so, what is the value of W? Unfortunately, it is a far from straightforward measurement to make. Instead, astronomers have had to combine 3 independent lines of evidence. By looking at light from supernovae, the CMB, the afterglow of the Big Bang, and the general structure of the universe, the most recent measurements put its value at -1.013. Yet while this is technically less than -1, it's so close to that value that it's within a margin of error. In other words, there is sketchy evidence that dark energy is indeed phantom, but so far not enough for the case to be compelling. And so should this calamity be avoided, what's the most likely alternative? Well, if dark energy's equation of state is indeed equal to exactly -1, we could be heading for what astronomers ominously call heat death. Dark energy will keep driving the expansion of the universe, but it'll never run away with itself. Instead, the universe will be gradually stretched ever more thinly. Galaxies move further apart, matter becomes diluted, radiation is stretched and cooled. It is a long, cold unwinding of all cosmic structure. Star formation will eventually cease as once great stellar nurseries fade away. All lights in the universe will flicker out. White dwarfs, the remnants of sun-like stars, will fade to black dwarfs. Black holes will gradually drip-feed their mass back out into the universe in the form of Hawking radiation. Indeed, eventually, the universe will reach an equilibrium so devastating that nothing new could ever form. Without hot versus cold, dense versus sparse, ordered versus disordered, the cosmos settles into a state of monochrome. And yet, unlike the Big Rip, this fate has no final moment. Time doesn't stop. Instead, it stretches on and on, possibly indefinitely. But an infinite future does carry its own brand of danger, one that's less obviously dramatic, but arguably even more unsettling. For creatures will appear in that long night, spectres will flicker out of the black, paradoxes that strike at the heart of our understanding of why time has a direction at all. These are mysteries beyond the expertise of the astronomer alone. They are questions only the philosopher can truly answer. As Big Ben chimes, fireworks tear into the sky above the River Thames. Rockets cascade in shoots of purple and red, golden sparks sizzle and crackle. But then, something strange happens. The trails of light suddenly converge. The sparks gather themselves back together. The fireworks unexplode. Fireworks are key to the way we mark the passage of time, used to celebrate big milestones in the collective calendar. But of course, we've never seen one in reverse. This may seem like common sense, but to a physicist, it's quite strange. This is because the equations describing motion, forces, and therefore fireworks work equally well either way. There's nothing in the laws of physics to prevent fireworks from unexploding. So why do we never see it? Why does time always seem to run forwards? The man who found the answer to this riddle was Ludwig Boltzmann, a 19th century physicist who saw the universe as a grand casino where the house always wins and time marches inextricably on. To understand Boltzmann's big idea, imagine a brand new deck of playing cards. All the cards are arranged in numerical order within their suits. Now imagine accidentally knocking the deck off a table so that the cards cascade haphazardly onto the floor. Then, one by one, you randomly gather them back up again. There's nothing to stop you from striking lucky and collecting them all back in their original order. It's just ridiculously unlikely to happen. There is, after all, only one specific way to do this. There are an awful lot of alternative configurations. How many exactly? Almost 100 undecillion. That's a 1, followed by 68 zeros. That's about the same as the number of atoms in the Milky Way. In other words, the chances of the deck randomly returning to its original state are the same as picking out a particular atom at random from an entire galaxy. And indeed, by thinking about atoms themselves in a similar way, Boltzmann explained why time always appears to run forwards. When it comes to time, physicists often talk about entropy. It's not the perfect description, but entropy is loosely a measure of how disordered a system is. A brand new deck of playing cards is a highly ordered system. In other words, its entropy is low. There is precisely one way to return the deck to this low entropy state, and there are 100 undecillion ways for the deck to become more disordered, for the entropy to increase. So it's not that an entropy decrease is forbidden or impossible. It's merely that it's very unlikely to happen, and on average you'd have to wait an extortionately long time to see it happen. Given our short lifetimes, and the relatively short period of time the universe has existed so far, we never do. It's perfectly possible for the atoms within a firework to conspire to make it unexplode, but don't bet on it happening anytime soon. And so according to Boltzmann, it's the fact that the probabilities are so heavily stacked in favour of an entropy increase that gives time a direction. The English astronomer Arthur Eddington later described this direction as time's arrow. Time, for us, only ever points forwards in the direction of disorder. And if time continues to run forwards indefinitely, then the future may well be infinite. And indeed, this isn't just a theory. Modern experiments have tried to catch entropy running backwards. The clearest example comes from something called nuclear magnetic resonance, where physicists work with trillions of atomic spins, the equivalent of tiny bar magnets hidden inside matter. Left to themselves, these spins behave like spectators drifting out of a stadium. They spread out and lose coordination. But with a carefully timed sequence of pulses, you can force them to turn around and refocus. For just an instant, the crowd comes back into alignment. It looks like the system has partially rewound itself. A brief, engineered reversal of disorder. But the effect is shockingly fragile. Any stray interaction, any imperfection in the pulse sequence, even the tiniest uncontrolled vibration destroys the reversal. The moment you stop actively shepherding the system, the natural drift into disorder resumes. And this same pattern shows up in more modern quantum simulators with trapped ions or ultra-cold atoms. In principle, the microscopic equations allow a rewind, but in practice, reality never cooperates for long. This may seem like a triumph for Boltzmann's theory, but his work still contains a hidden assumption, one that someone very close to him spotted almost immediately. His former teacher, Joseph Loschmidt, pointed out a brutal flaw. Imagine that instead of a pristine, perfectly ordered deck of cards, you start with one that has been thoroughly shuffled into maximum randomness. Now drop that pack of cards onto the floor and pick it up. This time, most of the outcomes are more ordered than what you began with. Entropy would decrease, and the arrow of time would point the other way. In that world, it would be exploding fireworks that seemed bizarrely unlikely. And so Boltzmann's explanation only works if you assume the universe, like a card deck fresh from its packet, began in a very special, highly ordered state. But the laws of physics don't demand that. They work perfectly well from any starting point, even ones that would make entropy fall rather than rise. And this became known as Loschmidt's paradox. Loschmidt's point was devastatingly simple. If you don't assume a special beginning, you don't get a special temporal direction. Loschmidt had shown that there's nothing in the laws of physics to force time to run forwards. If the equations work equally well in reverse, a universe without a special beginning could just as easily drift backwards. But even that wasn't the deepest problem, for Loschmidt had shown that the arrow wasn't guaranteed, but he hadn't actually explored how an eternal universe would behave. That breakthrough would come from Henri Poincaré, and with his work, we would begin to question the very structure of time in an eternal cosmos. In 1890, Poincaré published a landmark paper, The Three-Body Problem and the Equations of Dynamics. Loschmidt had shown that nothing in the laws of physics forbids time from running backwards. Poincaré now went further, proving a remarkable theorem. He showed that in any finite system obeying reversible laws, those reversed states are not just possible, they are inevitable. Given enough time, the system must eventually return to configurations arbitrarily close to ones it has visited before. This meant that if the future was infinite, the universe would be guaranteed to loop back on itself, not by destiny or design, but simply because a finite cosmos can only reshuffle its contents in so many ways. Eternity would eventually force every combination to return. The same stars, the same planets, the same galaxies, seemingly risen from the dead. In Poincaré's universe, this repetition is mathematically unavoidable, even more certain than night following day. Taking into account the size of the universe and the amount of things in it, its Poincaré recurrence time is roughly 10 to the power of 10 to the power of 10 to the power of 2.08. Years, days, or seconds. At that scale, the unit doesn't even matter. It is a huge amount of time. And yet, if the cosmos has infinite time to explore and repeat every allowable configuration of atoms, then time's arrow and even the notion of cause and effect begin to dissolve. And it was precisely this implication that horrified Boltzmann's critics. If recurrence is unavoidable, then the entire explanation of time's direction becomes shaky. The universe would spend most of eternity in meaningless repeating fluctuations, rather than the smooth, orderly arcs that usually make physics intelligible. And one man in particular took aim at this increasingly fragile account of time's arrow: Ernst Zermelo. Zermelo was a human scalpel, making a name for himself by attacking problems with a surgical precision. And where Loschmidt had attacked Boltzmann's assumptions, Zermelo attacked the consequences. He took Poincaré's recurrence theorem and drove it to its logical endpoint. If recurrence is guaranteed in any finite reversible system, Zermelo argued, then entropy cannot rise forever. In an eternal universe, entropy must eventually fall. Again and again, and not as a rare exception, but as an unavoidable feature of infinite time. Loschmidt had shown that Boltzmann's argument unfairly rested on a special beginning. Zermelo now argued that even if Boltzmann fixed that flaw, his conclusion could never survive an infinite future. Recurrence would eventually force the universe to revisit lower entropy states. And if entropy sometimes falls, then the arrow of time, the very thing Boltzmann had claimed to explain, cannot be derived from the laws of physics. It collapses the moment you give the universe infinite tomorrows. In a sense, Zermelo was questioning whether before and after can have any absolute meaning in an eternal universe. And this is where the astronomer completely bows out. What follows next belongs purely to the philosopher. Because mere months before Boltzmann published his ideas about the direction of time, one man had already followed its consequences to their most unsettling end. A political prisoner who realized that if time is infinite and the universe finite, then the cosmos must contain not only repetition, but endless copies of you. Smoke hangs low over the Parisian streets. In the Rue Saint-Denis, students and workers hurl stones at the municipal guards. And amid the chaos stands a thin, determined 22-year-old, Louis-Auguste Blanqui. Suddenly, he takes a bullet to the neck and collapses to the ground. However, Blanqui survives the ordeal, and indeed he would be injured 3 times that year, 1827, protesting against the restored Bourbon monarchy. A full-blooded revolutionary socialist, Blanqui would later be sentenced to death for his part in an 1839 insurrection. His punishment subsequently commuted to life imprisonment. He would escape, only to be recaptured and then released once more. In total, Blanqui spent over 35 years of his life behind bars. Or should that be this version of his life? In 1871, Blanqui found himself the sole inmate at Fort de Tauro, an island prison overlooking the Bay of Morlaix. Each day, the waves returned to batter the walls exactly as they had the day before. Alone in that repetition, Blanqui began to wonder whether the universe might be doing the same, endlessly replaying itself again and again. And Blanqui's prison ruminations became a book, Eternity According to the Stars. He'd been inspired in part by his view of human history. He believed that history was doomed to repeat because there were only so many options. Eventually, the same events are fated to reoccur. Blanqui was also an armchair astronomer, acquainting himself with star catalogues and tales of sprawling nebulae and distant cosmic systems. And so amid the isolation of his island prison, he fused these two ideas. His book describes a universe made from finite materials, endlessly rearranging into familiar patterns across the heavens. Every human being is thus eternal in every second of its existence. What I write here in my cell at the Fort of Tauro, I wrote and will write under the same circumstances for all of eternity. In other words, you are but a collection of atoms. Given enough time, the universe will conjure exactly the same atoms in an identical configuration. Not only that, it will do this over and over again. In a universe with infinite time, you were guaranteed a form of immortality. And perhaps above all others, one philosopher explored how it might feel for your life to repeat endlessly for eternity. Friedrich Nietzsche. What if a demon were to steal into your loneliest loneliness and say to you, this life as you now live and have lived it, you will have to live once again and innumerable times again, and there will be nothing new in it, but every pain and every joy and every thought and sigh and everything unspeakably small or great in your life must return to you, all in the same succession and sequence. And so, what if every moment of your life must return again, identically, for all eternity? Would you curse that fate, or embrace it? All of this leaves us in a peculiar position. Indeed, not everyone could live with a universe that loops without end. But for one figure, the prospect is particularly repugnant. For we now turn to the angel. What do they see when they look into an eternity that never lets anything die? And the angel, which I saw stand upon the sea and upon the earth, lifted his hand to heaven and swore that there should be time no longer. In the silence of the Sistine Chapel, the scaffolding creaks. A small oil lamp throws a trembling light onto fresh plaster as Michelangelo Buonarroti lifts his brush. He's in his 60s now, greyed and wrinkled by the relentless passing of time. Indeed, it's been nearly 25 years since he painted the famous ceiling of this room hidden away inside the Vatican. Back then, he'd illustrated the moment God first sparked life into Adam, but now his attention is turning towards the end of time. Eventually, Michelangelo sets down his brush. After 4 long years, this latest project is finally finished. Taking up the entire altar wall of the Sistine Chapel is the Renaissance master's depiction of the Last Judgment. Jesus has returned to the earth in final and eternal judgment of humanity. The dead are stirred from their graves, their morality weighed. Some ascend to heaven, others descend into hell. And so in Michelangelo's universe, earthly time does not loop. It does not repeat. It ends. And when it does, every act is tallied. Every choice has weight because it will never reoccur. you have but one shot at piety. Religious scholars and philosophers call this idea eschatology, the science of last things. Eschatology is a common feature of the Abrahamic religions. Christianity's Book of Revelation, Islam's Qiyamah, and Judaism's Yom HaDim all imagine time flowing towards a singular, irreversible endpoint where justice is finally dispensed and history is allowed to close. The eschatology of cyclical Eastern religions is a little different, but still present. Take the Hindu tradition, in which the present age ends when Kalki, the final avatar of Vishnu, arrives astride a white horse to bring the Kali Yuga to a close, after which the cosmos is renewed and the great cycle begins again. And so in these worldviews, time acquires meaning only because it finishes. Modern cosmology, however, is far less merciful. Indeed, Poincaré showed us that in a universe with infinite time and only finite ingredients, nothing is ever truly finished. Given enough time, the atoms that once formed your body must assemble again in precisely the same configuration, and so somewhere in the far and infinite future, the dead will rise. Not because a god has summoned them for judgment, but because the Church of Statistics demands it. The same bodies, the same thoughts, the same sins. Every moment will reappear, every kindness, every cruelty, every betrayal, every mercy, and then it will do so again and again and again, spooling on a never-ending tape. But in a universe where every life is no longer lived just once, how can there be judgment? After all, your actions are predestined, doomed only to repeat. In such a world, morality itself evaporates. To the angel, this is blasphemy, just one of the things that horrifies it about infinite time. And indeed, in terms of horrors, that is just the beginning. A heat-dead universe is extremely dilute. Any remaining matter is spread wafer-thin. The universe's temperature approaches an unfathomable low. Space is almost completely empty. Almost. For it will still contain quietly fluctuating quantum fields. Even heat death cannot calm them completely. In a universe with a low but finite temperature and infinite time, every possible quantum fluctuation will eventually occur, even Boltzmann fluctuations. These are spontaneous, random rises of order out of disorder due to an improbable but possible rearrangement of the microscopic realm. Of course, most of the time, these fluctuations will lead to small changes, a brief increase in the density of matter in a small part of space, a temporary photon, a momentary particle-antiparticle pair. But, occasionally, in an infinite universe, larger fluctuations are bound to occur. And the most famous example of this is perhaps the most disturbing prospect of all. A Boltzmann brain. A fully working mind, temporarily assembled from the chaos by chance. A fleeting consciousness, complete with memories it never lived. Counterfeit thoughts, feelings, and emotions. A fake sense of self floating in the eternal void, existing for a split second, then lost to the black. And so now the question is, statistically, which is easier to pull off? A temporary consciousness summoned by a chance quantum fluctuation, or one that's the child of a real brain sculpted by billions of years of evolution on a planet that needed billions more years of stars making heavy elements from which to build it? The grim truth is that the more time there is, the more the vast majority of conscious experiences will belong to Boltzmann brains, and not biological ones. Indeed, in a universe that lasts forever, it becomes dramatically more likely that you, the you experiencing these words right now, are one of those fluctuations. Ordinary beings, born from stars and shaped by genuine histories, become the rare exception. To quote Carl Sagan, if you wish to make an apple pie from scratch, you must first invent the universe, and so perhaps it would be easier for one to simply appear from nowhere. And so, do you actually exist? Are you sure? Or is the world you see around you a mere figment of quantum eternity? These thoughts may be enough to trigger an existential crisis, but the situation is far worse for the angel. How do you weigh actions taken by a mind that has only existed for a moment? How can you judge a life that was never actually lived? An eternal universe becomes not a place of judgment and reckoning, but one where endless consciousnesses drift unmoored through statistical noise beyond the realms of morality. And infinite time does not stop there. Anything that can happen will. Ghost planets, complete with mountains worn smooth by fictional erosion, hiding fossils within them from creatures that never lived, all illuminated by light from stars that never burned. Even entire galaxies and universes would be summoned from the statistical fog. Nothing forbids these configurations, they are only wildly improbable. But of course the notion of wildly improbable collapses under the weight of infinite time. And so only a universe with a real ending can avoid these spectres and comfort the angel. If time ends, truly ends, Poincaré loops die, Boltzmann brains are limited, moral action regains weight, and judgment becomes possible again. And yet for the angel, that is still not the end of the danger, for there are more quantum devils lurking in the shadows, and perhaps none more bizarre than the prospect of quantum immortality. In a windowless room, a volunteer sits hunched over a cold metal table. In front of him is a big red button. Through the tannoy from a neighbouring room, an anonymous technician explains that the button is harmless. The anonymous technician is lying. For pressing the button triggers the quantum measurement of an electron. Electrons have a property called spin that can either be up or down. It's the quantum equivalent of a coin toss. The chances are 50-50. If the outcome is up, a poison is released into the room and the volunteer dies. If the outcome is down, the poison isn't released and the volunteer survives. Nothing happens and the man lives to press the button another time. Thankfully, of course, this is only a thought experiment, but the fact that the outcome hinges on a quantum measurement could lead to a truly uncomfortable situation for the angel. In a classical, non-quantum universe, the volunteer will always die, eventually. Assuming he continually hits the button, after 100 presses, the odds of survival are just 1 in a million trillion trillion. But the introduction of a quantum measurement may change those odds. For there is one version of quantum physics that paints a significantly different picture: the many worlds interpretation. It says that whenever the universe faces a 50-50 quantum choice, it splits into 2 copies of itself. Both outcomes occur, just in 2 different branches of reality. Clearly, your consciousness can only continue in branches where you don't die. If the electron spin is up, your consciousness will immediately cease. But there's always another reality where the outcome was down, and that's the only branch in which your consciousness can logically go on. And so after 100 button presses, there's guaranteed to be one version of you that survived them all, even though you died in all the other branches. In other words, if your life hinges on a quantum measurement, it is impossible for you to die. There will always be a version of you that survives even 1,000,000 button presses. You are effectively immortal. Immortality without moral weight destroys everything the angel stands for. In a universe that contains infinite branching over infinite time, every conceivable crime and moral indiscretion is committed. Virtue didn't save you and vice didn't doom you. Moral courage is worthless. Moral cowardice unpunished. Even death loses all meaning, because you always escape it somewhere. However, not everyone buys this idea of quantum immortality. most physicists don't. This is because it depends entirely on a specific reading of quantum mechanics, the many worlds interpretation for which there's still no experimental evidence. Nor has any experiment ever confirmed that consciousness tracks only the surviving branches. And so perhaps this really is a step too far into eternity. The angel's horror is palpable, but its existential search for an ending also exposes a deeper uncertainty. We have spoken as if time were a river that might speed up, slow down, bend, or finally run dry. The angel has to believe in such a river because judgment requires both a beginning and an end. But not everyone agrees that time flows. Some claim that the river is frozen, that every moment, past and future, already exists. If so, time cannot end because it never truly began. And on the Orloy clock, one figure knows this better than anyone. The chronicler doesn't measure time, he records it. All of it. And in his book, every page is already written. A vast parchment lies unfurled on a vintage mahogany table. The paper is dishevelled, its surface discoloured. At first glance, it looks like an antique world map, but the labels look out of place. Rome, the Ides of March. London, the Great Fire. Philadelphia, Declaration signed. Hiroshima, the first flash. New York, falling towers. The distances make no sense. Hiroshima sits closer to New York than Rome does to London. And that's because this isn't a map of where things are, but when things happened. A map of history, not geography. The map is the work of the chronicler. But he has a secret that is hardly ever shared. The map is already finished. He doesn't need to add new events as they occur, because there are no new events to record. On a map of the Earth, there's no new terrain to add, it's all there in its entirety. Flying from Sydney to London doesn't mean the Australian city suddenly disappears, nor does London magically materialise only as the plane begins its final descent. All locations on Earth exist alongside one another, no matter where we happen to find ourselves on the map. And this is also the case for the map of time. Every moment, past, present and future, is already there. These events are simply different locations on the same vast temporal terrain. And so this means that on the map of time, standing in the present doesn't make it any more special than standing on the Greenwich Meridian. The present may be a useful reference point, but it's merely another moment. All past and future events exist fully and completely. This idea, known as the block universe, is based on Albert Einstein's theories of relativity. And to understand its implications, picture a simple loaf of bread. In our everyday lives, time seems like a series of consecutive moments. Those moments are like slices of the bread. Tomorrow dawns and a new slice is somehow added to the loaf. But the block universe theory argues that the loaf is already fully formed. Slices can never be removed, meaning yesterday doesn't simply vanish. The past is still there in its entirety. But then no new slices can be added either. The whole of the future is there too, every bit as real as the slice we call today. If you could see the loaf from the outside, it would look like one vast, unchanging block. Hence the name of the theory. And if that's not unsettling enough, Einstein's relativity does not merely say that different observers see time differently. It says that they move through it differently, too. Each observer traces a path, a world line, through the block. Along that path, events appear ordered. Cause precedes effect, entropy rises, time seems to flow. But the arrow of time is not written into the block itself. It belongs only to the path. This means that for someone on a very different world line, what counts as past and future would be rearranged. Our tomorrows could be their yesterdays. This perspective dramatically reframes the worries of the astronomer, the philosopher, and the angel. They feared what lies ahead, but here, ahead is nothing more than a local illusion. From another vantage point, the things they dread have already happened, or never happen. In a sense, the trio are arguing over the length of a river that may not exist as a river at all. To the chronicler, there is no gradual unfolding, no countdown, no approaching catastrophe. There is only a completed map. Einstein's general theory of relativity is arguably our best, most scientifically verified theory of all time. It underpins the block universe, but it's not the only show in town. Quantum mechanics is the other towering pillar of modern physics, and the two are famously hostile bedfellows. At the heart of this discord is a fundamental disagreement about the nature of reality. Try and combine the two theories together, and the equations quickly crash into an avalanche of infinities. But back in the 1960s, two men tried to circumvent this problem by attempting something wildly ambitious, writing down a single equation that describes the entire universe. It all started in 1965, when physicists John Wheeler and Bryce DeWitt met in Raleigh-Durham Airport when Wheeler was waiting for a connecting flight. Between them, the pair would eventually write down what is now known as the Wheeler-DeWitt equation. And this equation is remarkable, but not for what it contains, but for what it doesn't. There is no mention of time. Usually, time is an indispensable part of a physics equation. It describes how variables change. But in a sharp, disturbing contrast, the Wheeler-DeWitt equation does not describe a universe that evolves in time, it describes a universe that exists all at once. No ticking, no evolution, no before and after. The universe, at its deepest level, seemingly, simply is. The astronomer worried about how long time will last, the philosopher was concerned about the ramifications of infinite time, the angel feared what an endless future would bring. But the block universe and the Wheeler-DeWitt equation suggest that there is no future waiting to happen, something the chronicler already knows. This begs an unavoidable question. If the universe is a completed map, why does it feel as though we're constantly moving across it? Why does there seem to be a present moment at all? To answer that, theoretical physicist Julian Barber takes the Wheeler-DeWitt equation more seriously than almost anyone else. Where most physicists treat the absence of time as a technical nuisance, Barber treats it as a revelation. His claim is stark. Time doesn't need to exist, not even as a hidden dimension beneath the surface. According to Barber, reality is not something that unfolds. It doesn't progress from past to future. Instead, he proposes that the universe consists of a vast collection of individual, timeless configurations he calls nows. Nothing moves between these nows. There is no cosmic conveyor belt carrying one into the next. No master sequence ordering them. They simply exist. Once again, according to Barber, these events are not points along a timeline, but places on a map. And crucially, there is no rule that says we must ever arrive at them. On a real map, both Paris and the Sahara Desert exist, but standing in Paris does not make visiting the Sahara inevitable. The existence of a Boltzmann brain elsewhere on the chronicler's map does not make it inevitable. Indeed, inevitability requires time to do the work. And according to Barber, time isn't required to exist at all. It only feels so vivid to us because some nows contain records. A photograph, a scar, a fossil, memories. Do the memories inside your brain require a real past to exist? Strictly speaking, they only require a particular configuration of neurons now. And so can you be sure that the past is not all in your head? Julian Barber's ideas are certainly radical. Indeed, not everybody is willing to go as far as saying time doesn't exist at all. But there is another approach, one that agrees the universe is indeed timeless at its most fundamental level, but then argues time emerges from the timeless quantum quagmire. Imagine a single molecule of oxygen trapped inside a box. We can talk about the molecule's speed, energy, or direction, but asking about its temperature is meaningless, because temperature does not apply to a single molecule. So let's zoom out until we can see 1 trillion such molecules bouncing around the box. Some are fast, some are slow, some collide with each other. But it's now incredibly difficult to track the motion of every molecule. And so instead, physicists have invented the concept of temperature as a shortcut. It is a measure of the average kinetic energy of all the molecules. Temperature is not a property of individual molecules. It is a statistical summary, a way of talking about a system without knowing every tiny detail. It is the story we tell about what's going on above a certain scale. And for physicist Carlo Rovelli, this is the way to think about time. He proposes that individual quantum events don't unfold against an external ticking clock. At that scale, reality is timeless. Like temperature, time is the story we tell to make sense of events only as things get bigger, as multiple quantum events interact. In this vision of the cosmos, time is not a thing the universe contains, but merely a tool we use to describe the universe once it becomes complicated enough. Physicists call these kinds of things emergent. Time and temperature not existing at the most fundamental level of reality, but eventually emerging as a result of complicated interactions. In a sense, it's like your heartbeat. Zoom in on your heart with a giant microscope and you'll see individual cells and maybe even individual atoms. Yet these atoms and cells are not beating. The thing we call beating only emerges as multiple cells work together. If time is similarly emergent, then asking whether time can end is like asking whether temperature can end. It's a question that suddenly sounds like complete nonsense. And so, we're left where we began, staring into tomorrow and realizing we don't know what kind of thing it is. Perhaps it's a real destination, waiting somewhere ahead, with heat death and its statistical ghosts lurking in the far distance. Or perhaps it isn't ahead at all. Perhaps tomorrow already exists, or never will, or exists only as a convenient story, told by creatures like us, moving through a universe too large to hold in one mind. Either way, the future remains an open question. For now, there is only this moment, the one we are living inside. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.